Can Earth rotation affect a plane's speed? Well, let's tackle the big idea first, the Earth's rotation. Our planet is constantly spinning on its axis from west to east, at a pretty incredible speed. At the equator, the surface is moving at over 1,600 kilometers per hour, or about 1,000 miles per hour. So it's totally reasonable to think that if you're flying in the same direction as that spin, you'd get a nice boost, and flying against it would be like swimming upstream. It's a very intuitive thought, and it's one of the most common explanations people come up with. But science often has a wonderful way of surprising us. The key thing to remember is that an airplane isn't flying in a vacuum. It's not flying outside of Earth's influence, rocketing through empty space where the planet spins beneath it. Instead, it's flying within our atmosphere. And that atmosphere, all the air, the clouds, the wind, is for the most part moving right along with the planet. It's held to the Earth by gravity, so it spins with us. Think of it like this: if you're on a train and you jump straight up, you don't slam into the back wall of the train car. You land in the same spot because you and the air inside the car are already moving at the same speed as the train. The same principle applies to an airplane. The plane takes off from the ground, which is rotating with the Earth. It then flies up into the atmosphere, which is also rotating with the Earth. From the plane's perspective, the ground isn't whizzing by underneath it because of the planet's spin. Everything inside this system, the plane, the air, the clouds, you, is already in motion together. So the plane's movement is relative to the air mass it is flying through, not relative to the spinning surface of the planet far below. It's a magnificent dance of physics, where everything is in a shared frame of reference. Because the atmosphere moves with the Earth, taking off and flying doesn't suddenly remove the plane from this rotating system. If it did, taking off would be an incredibly wild ride. The moment you lifted off, the ground would race away eastward beneath you at hundreds of miles per hour. But that doesn't happen. The plane carries the momentum of the Earth's rotation with it. So just like jumping on that train, the plane's flight isn't directly helped or hindered by the simple fact that the planet is spinning. The real answer isn't about the solid ground below, but the fluid air all around. So, we can put that idea to rest. The Earth's rotation itself isn't what gives eastbound flights a speed advantage. It's a much more dynamic and fascinating process happening high up in the sky. The spin of the Earth does play an important indirect role by influencing weather patterns and creating the very thing we're about to talk about. But it's not a simple case of flying with or against the rotation. We need to look higher, into the powerful, high-speed winds that circle our globe. And that, my friends, is where the real secret lies. So, if it's not the Earth's spin, what is it? The answer is a spectacular meteorological phenomenon known as the jet stream. Imagine a fast-flowing narrow river, but instead of water, it's made of air. And instead of being on the ground, it's meandering high up in our atmosphere, typically at the altitudes where commercial jets fly, around 9 to 12 kilometers, or 30,000 to 40,000 feet. These are not gentle breezes. Jet streams can have wind speeds of over 160 kilometers per hour, and in some cases, they can exceed 400 kilometers per hour. That's faster than many race cars. These powerful winds are primarily caused by two things: the sun's heating of the Earth and our planet's rotation. The sun heats the equator more than the poles, creating a large temperature difference. This difference causes air to move, with warm air from the tropics trying to travel toward the colder poles. But because the Earth is spinning, this north-south movement gets deflected by something called the Coriolis effect. In the northern hemisphere, this effect pushes moving air to the right, and in the southern hemisphere, it pushes it to the left. The result of this deflection is that the winds tend to flow from west to east, creating these powerful jet streams. Now let's think like a pilot. If you have a massive river of air moving eastward at, say, 200 kilometers per hour, what would you do? If you're flying east, you'd want to get right in the middle of it. By flying within the jet stream, the plane gets a massive push from behind. This is called a tailwind. It's like being on a moving walkway at the airport. You're walking at your normal speed, but the walkway is also moving you forward, so your speed relative to the ground is much faster. This means an eastbound flight gets a significant boost, covering more ground in less time. Let's use our New York to London example. This is a classic eastbound route. Pilots will intentionally navigate their flight path to catch the powerful North Atlantic jet stream. This tailwind can shorten the flight time by an hour or even more. But what happens on the return trip, flying from London back to New York? Now, the plane is flying west, directly against this powerful river of air. This creates a headwind, which is like trying to run into a strong wind. It slows the plane's progress over the ground, meaning the flight takes longer and burns more fuel. So pilots flying westbound will do the opposite. They'll try to find routes that avoid the strongest parts of the jet stream. They might fly at a different altitude or take a more northerly or southerly route to find areas with weaker headwinds. It's a constant strategic game played with the atmosphere. Flight planners and pilots use complex weather models to map out the jet streams every single day, planning the most efficient routes possible. It's a beautiful example of humans working with the forces of nature to make travel more efficient. It's not about fighting the planet, it's about understanding it. This brings us to a really important distinction, a concept that's at the heart of understanding this whole phenomenon: the difference between airspeed and ground speed. It might sound a bit technical, but it's actually quite simple when you break it down. An airplane's speed is measured in two fundamental ways. The first is its airspeed, which is the speed of the aircraft relative to the air it is flying through. This is what the plane's own instruments, like the pitot tubes, measure. For a commercial jet, this speed is kept relatively constant, usually around 880 to 930 kilometers per hour, or 550 to 580 miles per hour. Think of the airspeed as the plane's effort. The engines are working to push the plane through the air at this consistent speed. The pilots set this speed to be optimal for fuel efficiency and the structural limits of the aircraft. So whether the plane is flying east or west, the pilots are aiming to maintain a more or less constant airspeed. The plane itself isn't going faster in the sense that its engines are working harder or it's pushing through the air any quicker. The effort remains the same. The real change comes from what the air itself is doing. This is where ground speed comes in. Ground speed is the speed of the aircraft relative to the ground. This is the speed that actually determines how long your flight will take. And ground speed is a simple calculation. It's the plane's airspeed plus or minus the speed of the wind. So, if your plane has an airspeed of 900 kilometers per hour and it catches a jet stream tailwind of 200 kilometers per hour, your ground speed becomes a whopping 1,100 kilometers per hour. You are cruising over the surface of the Earth at an incredible rate. Conversely, on the flight back, your plane is still maintaining that same airspeed of 900 kilometers per hour. But now it's flying into a headwind of 200 kilometers per hour. The wind is pushing against the plane, slowing its progress over the ground. So, your ground speed is now the airspeed minus the headwind, 900 minus 200, which equals 700 kilometers per hour. The plane is putting in the same effort, flying at the same speed through the air around it, but its actual progress across the planet is significantly slower. This is why the westbound flight takes so much longer. So, the plane's speed doesn't really change, but its velocity relative to your home on the ground does, and that's what matters for your travel time. It's a wonderful illustration of relative motion, a key concept in physics. The experience of speed depends entirely on your frame of reference. For the pilot, the airspeed is key. For the passenger, eager to get to their destination, it's all about the ground speed. Understanding this difference is the final piece of the puzzle to understanding why your flight time can vary so much depending on which direction you fly. So, there you have it. The next time you're on a flight that seems unusually fast or slow, you'll know why. It's not an illusion, and it's not because you're racing against the planet's spin. The truth is written in the wind, specifically, the powerful high-altitude jet streams that circle our globe. A plane does not fly faster just because it's going west. In fact, it's usually slower due to headwinds created by these very jet streams. The Earth's rotation plays its part by creating these winds, but it's the winds themselves that do the pushing and pulling. Flying east is generally faster, thanks to tailwinds from jet streams that act like a massive invisible conveyor belt in the sky. Pilots are expert navigators of these atmospheric rivers, charting courses to either ride them for a boost or dodge them to avoid being slowed down. It's a fantastic interplay of physics, meteorology, and human ingenuity that makes global air travel possible and efficient. The plane's own speed through the air, its airspeed, stays about the same, but its speed over the ground can change dramatically. The world is full of these amazing, interconnected systems, from the way the sun heats our planet to the spin of the Earth and the resulting currents in our oceans and atmosphere. It's all one big, beautiful, scientific dance. And by understanding it, we can work with it. So thank you for coming on this journey with me today. Keep looking at the world around you, keep asking questions, and keep being curious, because science is everywhere, and it's for everyone. Until next time, fly safe.